We're now going to go to the last section of the reading that you did, which is on the notion of power. And power is the idea of the rate of change, the rate at which a force is doing work on a system, or at least that's the limited idea of power we're going to cover in Physics 110. So if a force is doing work on a system, it might do that amount of work in a very short period of time, so it does it at a great rate, or it could do the same amount of work over a much longer period of time, and that would be sort of a lower power. We want to make that notion definite. So the power output of a force is the rate at which that force is doing work on the system. Of course, as always, we've got to be careful to define what our system is. In terms of how we speak about it, we might say that the force delivers a certain power to the system or outputs a certain power. Sometimes people talk about the power output of a certain device or an electrical device. The SI unit for power has the units of work divided by time, so joules divided by seconds, but a watt is the simplified unit for that. So 1 watt is 1 joule per second. Positive power we can think of as means the external force is doing positive work on the system, and another way to think of that is energy is being transferred into the system, and it's going to manifest itself as a change in the internal energy state of the system. So in terms of our most recent work-energy relationship, here I put all the internal stuff on the right-hand side. So I took that net work done by non-conservative internal forces, put it on the right-hand side with a minus sign. And we can think of this as being the energy that's being transferred into the system from the environment. The change in kinetic energy and the change in potential energy are kind of a way to think of the change in the internal energy of the system. The system can store energy in terms of mass, pieces of mass that are moving around. If they're moving, they're sort of storing energy that way. Or in terms of a springy internal force, they might store it as a potential energy. And the work done by non-conservative internal forces is always going to be negative itself. That means the negative of that work will be something positive. And this relationship says, however much energy the force is transferring into the system, that energy might show up as changes in the energy state of the system, or it might be lost to a friction type force. So however much energy is lost to the friction type force, whatever's left over manifests as a change in kinetic or potential energy of the system. Similarly, negative power, if a force is doing negative power on a system, that means that energy is being transferred out of the system and into the environment. So in that case, maybe the system is losing potential energy, and as it does, it's not speeding up, so it's not gaining potential energy, but it's actually doing work on the environment. That we could see that happening in an example. So let's figure out how to work with this definition. The average power, we're going to first define what average power is, and then transition from average power to instantaneous power, as we've done so many times in this course. The average power delivered to a system by an external force in a certain amount of time, delta t, is defined to be the work done by that force in time delta t divided by delta t. So it represents the average rate at which the force is doing work. So here's an example. I lift a 3 kilogram block upward at constant speed. So I'm raising it at a constant rate further and further from the surface of the Earth. And we know it moves up a half a meter in 2 seconds. In this case, in order to analyze this, I want to figure out how much power, average power, my hand is delivering or transferring to the system as time goes on here. At what rate is my hand delivering power to the system? I need to be clear about the system first, so let's take the example of just the system being the block itself. In this case, there are 2 external forces that are acting on the block, my hand force and the gravitational force. Let's consider the average power delivered to the block by my hand force first. It's delivering an average power of, well, I've got to calculate what the work done by my hand force is, and my hand force, if it's going up at constant velocity, my hand force has to exactly balance out what the gravitational force is, in other words, the weight force, because it's not accelerating. And so when we calculate the work done by the hand force, I can just calculate the magnitude of the force of my hand is just mg, because the acceleration is 0 if I'm moving it up at constant velocity. So I'm going to calculate the work done as force times distance, because my hand force is going to be constant, and divided by the time it took. Okay, so my hand force has to counteract gravity, so it counteracts mg, 3 times 9.8, and we've moved a half a meter upwards, and that all happened in 2 seconds. So this is the work done divided by the time it took. That's 7.35 watts, the rate at which work is being done by my hand on average as I'm raising it up. Similarly, for the same system, the gravitational force is another external force that's delivering power to the system, and we can calculate the average power due to the gravitational force. And we'll do it exactly the same way. The only difference is that the work that's being done is negative work in this case. So the force is exactly the same. It's still 3 times 9.8 because my hand force has to balance out the weight force. So in this case, the weight force is the same, but it's negative work that's being done by gravity. It's pulling down as the block is being raised upward. So it does negative work in the same amount of time. So the gravitational force is delivering minus 7.35 watts of power to the block. Together, we can see that no net power is being delivered to the block. Okay, my hand is delivering positive power to the block, but gravity is delivering negative power to the block. And therefore, no energy is being transferred to the block, and the only way the block, since it's a particle, the only way it can store energy is as kinetic energy, and so if we're not delivering any power to it overall, that means it shouldn't change its kinetic energy. And in this case it doesn't, of course, because I'm raising it at a constant speed. So that makes sense in terms of the work kinetic energy theorem. Let's choose now a different system for the same scenario. Suppose I take my system to be the block plus the Earth, where the gravitational force is an internal force pulling between the block and the Earth, and my hand force I'm going to think of as external. In this case, we shouldn't be calculating the power delivered to the system by the gravitational force. That's an internal force. It's not being delivered from the environment. But my hand force is, and the calculation looks exactly the same. My hand force hasn't changed. Everything's the same as it was before. So my hand is delivering 7.35 watts of power to the system as time goes on, and there's no other forces that are delivering negative work, negative power to the system as time goes on. That means the system's gaining energy, and in this case that makes sense because even though it's not gaining kinetic energy, it is gaining potential energy as I move the book further and further from the surface of the Earth. So the system's gaining energy even though we don't see it as kinetic energy in this case. It's not gaining kinetic energy, but it gains gravitational potential energy. Now that was the notion of average power, just work done divided by the time it took to do the work. But there are a lot of cases where the rate at which a force is doing work could change with time. So I could be lifting a block up slowly and then all of a sudden start lifting it much more quickly. And we would want to say that the instantaneous power has increased delivered to the block system by my hand if I speed up the rate at which I'm raising it. So we need a notion of instantaneous power, and here's how we're going to get to it. We're just going to calculate the average power of a constant force being exerted on an object as it moves in a different way. So we're going to imagine whatever way the object is moving, let's call that direction the x direction, and we'll calculate the work done by a constant force as Fx times delta x, one of the very first formulae we did in this chapter. So this work done divided by the time it took, and now we can see that delta x over delta t there is the same thing as the average velocity, and if the velocity is not changing, that's the same thing as the instantaneous velocity. This expression, even though we use the average power formula, makes sense as an instantaneous formula. So we're going to think of the instantaneous power as just instantaneous power delivered to the system by an external force, Fx as it moves along the x direction, and the point at which the force is being applied to the system is moving at velocity v, or speed v, Vx along the x direction, the instantaneous power is just Fx times Vx. So with the same force, the larger the speed at which the point is moving where the force is being applied, the larger the rate of power that is being delivered to the system from the environment, or being delivered to the environment by the system if it's negative. Why don't we, I don't have this on a worksheet, but let's think of it as a worksheet problem. So I'll pause the video and give you a chance to think about it. Here's a 400 kilogram block being pulled up a frictionless inclined plane, so it's free to slide easily along the plane. But of course, if this rope force is going to pull it up the plane, it has to counteract the force of gravity. So the idea is we're going to pull this thing up at a constant speed of 2 meters per second along the plane direction. The plane is inclined at 20 degrees to the horizontal, and there's a rope connected to me. You can think of this as like a winch up at the top. If you know a winch that pulls, a truck, if a truck gets stuck in the mud or something like that, you attach a winch to a tree to pull it out. This is the same kind of thing. What is the power output by the winch, or you can think of it by the rope force, to the system, which is defined as the block plus the earth? So we're not going to consider the inclined plane as part of our system, but the only objects in our system are the block and the earth down below, and we'll consider the gravitational force to be an internal force. But the normal force and the rope force, they're both forces that are acting on a moving part of the system as it moves along. We'll consider those to be external. What's the power output of the winch? That gives us something important to know, because it tells us, how much power whatever electrical outlet this thing is plugged into is going to have to output. So it tells us something practical we might need to know. So try that yourself on a piece of paper, and I'll be back with the solution.